Good day, ladies and gentlemen. This is Genevieve B. Portarkis, and today I will be sharing to you my knowledge about simultaneity and relativities of time, length, and velocities. So, simultaneity considered how we measure elapsed time. If we use stopwatch, for example, how do we know when to start and stop the watch? So one method is to use the arrival or light from the event, such as observing a light turning green to start a drag race. So the time will be more accurate if some sort of electronic detection is used, avoiding human reaction times and other complications. So time dilation is the phenomenon of time passing slower for an observer who is moving relative to another observer. Suppose, for example, an astronaut measures the time it takes for light to cross her ship, bounce off a mirror, and return. How does the elapsed time an astronaut measures compare to the elapsed time measured for the same event by the person on Earth? We find that the elapse of the time for the process depends on who is measuring it. So in this case, the time measured by the astronaut is smaller than the time measured by the Earth-bound observer. The passage of this time is different from the observer because the distance of light travels the astronaut's frame is smaller than the Earth-bound frame. So light travels at the same speed in each frame, and so it will take longer to travel and greater distance in the Earth-bound frame. So length is one thing all observers agree upon is relative speed. So even though clocks measure different elapsed times for the same process, they still agree that relative speed, which is distance divided by the elapsed time, is the same. So this implies that distance too depends on the observer's relative motion. If two observers see different times, then they must also see different distances for relative speed to the same to the same to each of them. So, for simplicity, we strict our consideration of velocity addition to one-dimension motion. Classically, velocity like regular numbers in one-dimensional motion.
The relativity of simultaneity is the concept that simultaneity, with the two events occur at the same time, is not absolute but depends on the observer's frame of reference. According to the theory of special relativity, it is impossible to say in an absolute sense whether two distinct events occur at the same time. If those events are separated in space, such as a car crash in London and another in New York, the question of whether the events are simultaneous is relative. In some reference frames, the two accidents may happen at the same time. In other frames, the crash in London may occur first, and still in other frames, the New York crash may occur first. If the two events are causally connected, then the relativity of simultaneity preserves the causal order. If we imagine one reference frame assigns precisely the same time at the same time to the events that are different points in space, a reference frame that is moving relative to the first will generally assign different times to the two events. This is illustrated in the ladder paradox, a thought experiment which uses the example of a ladder moving at the high speed through a garage. In 1905, Albert Einstein abandoned the ether and emphasized the significance of relativity of simultaneity to our understanding of space and time. He deduced the failure of absolute simultaneity from two stated assumptions: the principle of relativity is the equivalence of inertia frames, such as the laws of physics apply equally in all inertial coordinate systems. The second one, the constancy of the speed of light detected in empty space independent of the relative motion of its resource.